The real zeros of a polynomial function. Chapter 4, Section 5. I want to introduce the division algorithm for polynomials. Now this is going to be wordy, I'll warn you about that. If f of x and g of x denote polynomial functions, and if g of x is a polynomial function whose degree is greater than 0, meaning that it's not a constant, then there are unique polynomial functions q of x and r of x such that f of x over g of x is equal to q of x plus r of x over g of x, or f of x is equal to q of x g of x plus r of x, where r of x is either the zero polynomial or a polynomial of degree less than that of g of x. So basically you can say you divide one polynomial by another, which we've done. We dealt with that with synthetic division and with long division, that you're going to end up with a quotient, and that's going to be a quotient function, q of x, and possibly a remainder, r of x. And here it points out r of x is either the zero polynomial, meaning you may not have a remainder, so r of x may be equal to 0, or it will be a polynomial of a degree less than that of what you're dividing by. So that gives us the idea that basically divide two functions and you're getting a quotient function and a remainder function. So let's put that to use. Let f be a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. Now this is interesting. So what that's saying is, if we divide a polynomial by a binomial x minus c, then the remainder of that division, that remainder function r of x, is just going to be f of c. So if we were to divide something by x minus 5, then we could just plug 5 into the function, and that'll tell us the remainder. And we'll do an example of this, don't worry. And then the factor theorem says, let f be a polynomial function, then x minus c is a factor of f of x, if and only if f of c is equal to 0. So basically saying if the remainder is 0, then x minus c is a factor. And if x minus c is a factor, then the remainder is going to be 0. Remember that if and only if thing says it has to work both ways. Let's determine if x plus 1 is a factor of x cubed minus 4x squared minus 11x plus 30. And we're going to use the factor theorem. So basically, we're going to divide it. So I'm going to use synthetic division just because it's easier. So I've got that. So I have 1, negative 4, negative 11, and 30. And I put my negative 1 there, working through. 1 comes down. 1 times negative 1 gives me negative 1. Negative 4 plus negative 1 gives me negative 5. Negative 5 times negative 1 gives me 5. Negative 11 plus 5 gives me negative 6. Negative 6 times negative 1 gives me 6. 30 plus 6 is 36. So we took a cubed and divided it by x. Therefore, we're going to have x squared as our starting term. So we have x squared minus 5x minus 6 plus 30x divided by x plus 1. Since there is a remainder, x plus 1 is not a factor. And I want to point out that we already looked at this, and q of x is equal to x squared minus 5x minus 6, and r of x is equal to 36. So we see that it has a quotient of x squared minus 5x minus 6 and a remainder function of 36. Well, let's look at the remainder theorem. The remainder theorem Find the remainder if x cubed minus 4x squared minus 11x plus 30 is divided by x plus 1. Now this is the same thing we just did on the other page. So we're going to put f of -1 in, so just substitute -1 for x, so we get -1 cubed minus 4 times -1 squared minus 11 times -1 plus 30. So f of -1 is equal to -1 minus 4 plus 11 plus 30. Be very careful of your signs when you're doing this. Remember, if you're taking a negative value and raising it to an odd power, it's going to be negative. If you take a negative value and raise it to an even power, it's going to be positive. So -1 cubed gave me -1. -1 squared gave me +1, but I was multiplying that by -4, it gives me -4. -1 times -11 gave me 11. So we come out with 36. And remember when we did this with our long division, not our long division, with our synthetic division, we came out with x squared minus 5x minus 6 plus 36 over x plus 1. So 36 was our remainder. Number of real zeros. A polynomial function cannot have more real zeros than its degree. It's impossible. You got a third degree polynomial function, it can't have more than 3 zeros. You have a 12th degree polynomial function, it can't have more than 12 zeros. Rational zeros theorem. Let f be a polynomial function of degree 1 or higher of the form f of x is equal to a sub n, x to the n plus a sub n minus 1, x to the n minus 1 plus et cetera, all the way down to a sub 1x plus a sub 0, where a sub n is not equal to 0, right? Because as soon as you make the leading coefficient equal to 0, that's no longer the leading term, it would come into the next one. And a sub 0 is not equal to 0. So we are going to have some constant term, where each coefficient is an integer. If p divided by q in lowest terms is a rational zero of f, then p must be a factor of a sub 0 and q must be a factor of a sub n. Say what? Basically what this is saying is that if we have a polynomial function, we can look at the leading coefficient and the constant term, factor those two values, and use them to find all of the possible rational zeros. It doesn't tell us that they are rational zeros, but it gives us a listing of all the possible rational zeros. So basically we take a sub 0, our constant term, factor it, find all its factors, and those are our values that we can plug in for p. We take the leading coefficient, a sub n, find all of its factors. Those are the values we plug in for q, do the division, and we get the list of all possible rational zeros. We can then go through and try them out and see which ones work and which ones don't. So the rational zeros theorem, let's put it to use. Use the rational zeros theorem to list all possible rational zeros of 2x squared minus 8x plus 15. Do not solve. All we're doing right here is we're just seeing what are the possible zeros. So first thing I'm going to do is I'm going to factor the constant term 15, and I'm going to take all of its factors and make them possible values for p. So 15 has 1, 3, 5, and 15. And don't forget that those numbers could be positive or negative. So p can be equal to plus or minus 1, plus or minus 3, plus or minus 5, or plus or minus 15. For q, I'm going to look at the leading term, that 2, and factor it. Well, the factors of 2 are 1 and 2. And remember, those can be plus or minus also. So q is equal to plus or minus 2 and plus or minus 1. Now to find all possible rational zeros, I'm going to take each of those p's and divide it by each of those q's. So I just start out and I work my way all the way through the p's with the first q, and then I go through all the p's over the second q. So you'll see that I have negative plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. That was putting them all over 1. And then when I put them all over 2, I get plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, plus or minus 15/2. Now, I will point out to you that if we were to go through and plug each of these in, so the way for us to determine whether any of these or which of these are rational zeros of this function would be that we would have to go in and plug in +1 and see what we get. Because if it is actually one of the rational zeros, we'll get 0 as the result. So if I plug in +1 here, I get 2 minus 8 plus 15, which is not 0. So obviously that is not a 0 of this function. Well, it does turn out that with this particular function, it does not have any rational zeros. But we came up with the list of possible ones. No other value could have even possibly been a rational zero to this. Descartes' rule of signs. Let f denote a polynomial function written in standard form, meaning descending order. The number of positive real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer. So if we have a polynomial function written in descending order, then all we have to do is look at the coefficients, and ignoring any zero coefficients, we want them all to be, we look at the change in sign. And we count the number of changes of sign in those coefficients, and that will give us the number of positive real zeros, or subtract 2, and that gives us the number of positive real zeros, or subtract 2. So basically, if we came out with the sign changed 5 times, we'd either have 5 positive real zeros, 3 positive real zeros, or 1 positive real zero, because we just get that number, the number of sign changes, and then subtract 2 until you get to the smallest positive number you can get, or I should say the smallest non-negative number that you can get. The number of negative real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of negative x, or else equals that number less an even integer. So same thought processes for positives, but now we plug in negative x. And then we look at the sign changes. So if we had 2 sign changes, then we could have 2 negative real zeros or 0 negative real zeros. Let's try it out. Use Descartes' rule of signs to find the number of positive and negative real zeros of f of x equals to 3x cubed plus 6x squared minus 7x minus 20. So to look for the positive real zeros, we're going to look at that function just as it is and look for the sign changes. Well, we have positive 3, positive 6, negative 7, positive 20. So that's plus, plus, negative, plus, right? So positive, positive, negative, positive. So it changes from a positive to a negative, and then from a negative to a positive. That's 2 sign changes, which means we have 2 or 0 positive real zeros. If we're looking at the negative, we're going to find f of negative x. So we substitute negative x, and we get negative 3x cubed plus 6x squared plus 7x plus 20. So we have negative, positive, positive, positive. Sign changes once from negative positive. So 1 sign change, which means we have 1 negative real zero. How about a couple theorems? Every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. So if we have a polynomial function with real coefficients, it's going to get broken down into either binomials, linear factors, ax plus b form, or irreducible quadratic factors, ax squared plus bx plus c. There's nothing else it can turn out to be. Example, f of x is equal to x cubed minus 3x squared plus 4x minus 12 factors into x minus 3 times x squared plus 4. Notice x squared plus 4, if it was x squared minus 4, then we could factor that, but it's x squared plus 4, so that's considered an irreducible quadratic factor. A polynomial function with real coefficients of odd degree has at least one real zero. Okay, remember it can be broken down into linear factors and or irreducible quadratic factors. Linear factors are going to give us a real coefficient, is going to give us one real zero. Those irreducible quadratic factors, those are going to, we'll get into in just a moment, those are going to give us two other zeros, but not necessarily real. So if we have an odd degree polynomial with real coefficients, then the fact that it's odd tells us that we're going to have at least one real zero. Bounds on zeros. What do I mean by bounds? Well, basically, if you're talking about real zeros or rational zeros, you're going to, at some point, hit a point where there's not going to be any more. You start at 0 and work your way towards infinity, or start at 0, work your way to negative infinity. At some point, it's going to be the end of where your zeros are. You're not going to have any zeros beyond that point. So we call those bounds. Let f denote a polynomial function whose leading coefficient is positive. If capital M, we tend to use M for capital M's for maximum in mathematics. If capital M is greater than 0, is a real number, and if the third row in the process of synthetic division of f by x minus m contains only numbers that are positive or 0, so non-negative numbers, then m is an upper bound to the zeros of f. Okay, so if we take some value, m, and we treat that as if it was a 0, so we divide by x minus m, our third row of the division, synthetic division, if all the values are non-negative, then we say it's an upper bound, which means there are not going to be any real zeros larger than that. Now, there could be another bound that's even closer to the values. This, if I plug in m equal to 25, I may find out that it's an upper bound. I could also plug in m equal to 10 and find out that it's an upper bound, because if 10 is an upper bound, that means there's not going to be any zeros beyond 10. So 25 is also an upper bound because there won't be any zeros beyond 25. So realize that there's not a set m. There are numerous m's that you can find, but obviously you don't want to get ridiculous and just always plug in 1,000,000 for m and say, hey, look, it's an upper bound, because there are times where that's just absurd. Now, lowercase m, we use lowercase m a lot of times for minimum, is less than 0 is a real number. And if the third row in the process of synthetic division of f by x minus m contains numbers that are alternate positive or negative 0 and negative or 0. So basically 0 can count into either side. So positive or 0 and negative or 0. So basically alternating from non-negative to non-positive to non-negative to non-positive, then lowercase m is a lower bound to the zeros of f, and similar idea to what I said about the upper bounds, that there are numerous values that you could plug in that would work. We're trying to get close to our zeros, but we don't have to fight within. So, okay, well, 5 worked. Does 4 work? Well, 4 works. Does 3 work? We don't necessarily have to beat our way down until we can't get any number closer. So let's try it out. Find an upper bound for the zeros of f of x. So yeah, f of x is equal to x cubed minus 3x squared minus 10x plus 24. So let's try m equal to 5. So m equal to 3. So capital M equal to 3. So I'm going to do synthetic division for this, plugging in our 3 as our capital M, and we get 1 plus 0 minus 10 minus 6. Now remember, for an upper bound, we're looking for all of these values to be non-negative. And I see negative 10 and negative 6, so contains negatives, it's not an upper bound. So let's try another one. What if we say m equal to 5? Well, if I plug that in, then I get 1, 2, 0, 24. Those are all non-negatives, so it contains no negatives. It is an upper bound. Doesn't necessarily mean that it's the smallest upper bound, but it means that there will not be any real zeros beyond that value. Let's go the other way and look for a lower bound. Remember, upper bound, you're looking for it to be non-negative for each of the coefficients. For lower bound, you're looking for it to be alternating non-negative, non-positive, non-negative, non-positive, and it could start non-positive, non-negative, non-positive, non-negative. So don't worry about the order, they just have to alternate back and forth. So we used 3 and that didn't work. We used 5 and that did work for upper bound. So I'm going to start with, let's make m negative 5. No guarantee that that's going to work, but it's a reasonable place to start. So I'm going to plug that in. I do my division. I get 1, negative 8, 30, negative 128. That's non-negative, non-positive, non-negative, non-positive, or it's just positive, negative, positive, negative. You don't have any zeros, so it makes it easy that way. The signs alternate, so that is a lower bound. And that's all we're looking for. Could we get closer? Would it work with negative 4? Maybe. That would be for you to go forward and look at. Okay, so I just want to point out these are not the only bounds, nor are they the closest, but we can guarantee that there are no real zeros greater than positive 5, and there are no real zeros less than negative 5. And in this particular case, the actual zeros to this are at negative 3, 2, and 4. So we could see that we could have taken lowercase m to negative 4 and it still would have worked. That would have been a lower bound. Intermediate value theorem. This is one of those things that sounds impressive until you really think about it and you go, yeah, of course that's true. So let f denote a polynomial function. If a is less than b, and if f of a and f of b are of opposite sign, there's at least one real zero of f between a and b. If you choose two values for x, and the outputs of the function at those two values change sign, then there's got to be a zero in there. It has to have crossed the x-axis. That's all it's saying. So let's try it. Use the intermediate value theorem to determine if there is at least one zero between 0 and 1 for f of x equal to 6x squared plus x minus 2. So I'm going to plug in 0. So f of 0 is equal to 6 times 0 squared plus 0 minus 2, which gives us negative 2. I plug in 1. F of 1 is equal to 6 times 1 squared plus 1 minus 2, which gives me positive 5. Sign is negative at the first value, 0. Sign is positive at the second value, 1. Therefore, the sign changes, and there's at least one zero between 0 and 1. That's all it's saying. Now, this will not necessarily catch or prove that there's always a 0 there, or that there isn't a 0 there. If we have an even number of zeros between those two values, then your sign's not going to change. So all this shows is if there is a sign change, then there's at least one zero. And it doesn't tell you how many. You can guarantee that there's not an even number of zeros, because if there was, then the sign wouldn't have changed. But all I can guarantee is if the sign changes, there's at least 1 0. So you could even say that to the point there's an odd number of zeros. But if the sign does not change, it doesn't tell us anything. Approximating the real zeros of a polynomial function. Okay, so what if we're looking at that and we say, okay, there is a 0 there. Where is it located? Like we look at this one and go, well, a sign changed. So there's a 0 between 0 and 1. Well, how can I approximate that 0? How can I find that 0? Well, how we can do that, first find two consecutive integers a and a plus 1 such that f has a 0 between them. So we did that there, right? We had 0 and 1. We showed that there was a 0 between them. Divide the interval into 10 equal subintervals. So you're just going to break that up so that 0 to 1 would become 0 to 0.1 to 0.2 to 0.3 to 0.4 to 0.5 to 0.6 to 0.7, 0.8, 0.9, 1, right? So we just break it into 10 subintervals. And we evaluate f at each endpoint of those subintervals until we see the sign change. So until the intermediate value theorem applies. When we see the sign change, we know that there was a 0 there. Once we do that, we divide that new interval. So if we were going this, we were at tenths. Now we're going to go down to hundredths in that interval where we know there's a sign change. We're going to do the same thing again. We're going to go through and apply the intermediate value theorem and keep using that until we find that it changes sign. And then we know it's in that interval. And you just keep doing that over and over again until you reach the desired accuracy. So we may want to make sure that we may want our 0 accurate to the nearest hundredth. Well, in that case, we're going to take it to the thousandths and find out where it fits in there because we need thousandths to round to hundredths. So just be careful. Whatever your accuracy is, you want to make sure you go one more decimal place so that you can round properly. And that completes chapter 4, section 5.